going to do this first problem today. We're going to find the rate of change in the angle of elevation of the camera shown in figure 2.535 at 10 seconds after liftoff. So if you imagine that you are capturing the launch of this rocket, and it's probably going to move pretty fast, and if your cameraman misses it, that will be sad. If on CNN we're watching our news and we see just like smoke because it didn't keep up with the rocket, that will be a disappointment, and you'll probably lose your job if you're the cameraman. So one way that could possibly be dealt with, I don't know if this is actually the case or not, is that you could have this programmed to follow at certain speeds there. So what we want to know is what this angle is going to be changing at. So we have a television camera at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation S equals 50t squared. Here, that rocket is accelerating. So, if you've ever watched footage of a rocket launching, you probably have, it seems like it's sort of slow at first, which is kind of weird, and then it takes off, and then it's going really fast, and you can't even really tell how much it's accelerating, because once it gets far away, it looks much slower than it really is. But we know this equation that it will be accelerating at. And S is measured in feet, T is measured in seconds. The camera is 2,000 feet from the launch pad. So we want to program our camera so that it will follow this pattern, so there's no chance that we're going to miss the marvelous moment whenever it launches here. So we are going to start with this equation right here. Tangent of theta equals S over 2,000. All right, because 2,000 is fixed, this camera is staying in one place. We know 2,000 feet from the base of the rocket does not change. So tangent would be opposite over adjacent. So S is your opposite side. Adjacent is the 2,000 here. So we're starting with that equation. Tangent of theta equals S over 2,000. Okay. So whenever we do this problem, make sure I'm not messing up. Second guessing myself on whether I need to plug that equation in before or after I take my derivative. Yeah. Okay, that's what I thought. Okay. So we need to take the derivative of this. What are we looking for?
S.
No.
Theta.
No. Okay. It says to find the rate of change in the angle. So it's not, the angle is theta, right? But we don't need to know theta because theta is changing, that camera is tilting upward. We need to find the rate of change of the angle, which would be d theta dt. Right? So we're going to have to take the derivative of this so that we can find d theta dt. Alright? What is the derivative of tangent theta? Secant squared theta, and what do we have to put with it? D theta dt equals, and we can kind of think of this, if you want to think of this, this is like 1 over 2,000 times S, right? So that we don't have to do a quotient rule here. So that 1 over 2,000 just stays there. What's the derivative of S?
ds dt.
ds dt. So we are wanting to know, it's the angle of elevation of the camera, the rate of change in the angle of elevation of the camera shown at 10 seconds after liftoff. So I know T equals 10. But I don't even have a T to plug in there. Alright. So, what could I do?
We have an equation S equals 50t squared.
I do.
So, in there to figure out S.
Okay, S equals 50t squared. So I can plug in 10 here. So S equals 50 times 10 squared, which is going to give me S equals 50 times 100, which is 5,000. Okay, so I know S is 5,000. So, I don't have an S in this equation, though. But I do need to find theta, right? Because I'm looking for d theta dt. I'm not going to replace d theta dt. But I need theta. I also need ds dt. So if I want to find theta, I need to go back to the original here. I know at 10 seconds, S equals 5,000, right? So that means tangent of theta equals 5,000 over 2,000. How do we find that?
What we move 2,000 times tangent or whatever?
Inverse tangent, good. So we'll do inverse tangent of 5,000 over 2,000. Let's see. Yeah, everything on the AP exam is radians, so just your calculator should be in radian mode. It's the default. So we're just going to stick with radians. I think I'm actually in same degree. So you should get theta equals 1.19. Yeah, 1.19028. Keep that number in your calculator. Don't round it off. You can round off what you write down, but keep it in your calculator. So that is theta at 10. On the 89, let me look up to see. It is mode and go down to the fourth one where it says angle. You have to go over and change it to radian, and then you have to make sure you hit enter so that it will save it, or it won't actually change it. On the 84s, you don't have to hit enter or anything. But if you hit mode, it should be there in radians. So we got the angle, that's good. We still have to find ds dt or we can't solve this, right? How could we find ds dt? We've got to go back to s equals 50 t squared, right? If I take the derivative of s, what do I, with respect to t, what do I get? ds dt. And if I take the derivative of this, I'll get 100 t, and then I would put dt dt with this, which really is just 1, so I don't have to write it. Alright, because this is actually, you're taking the derivative with respect to that time there. So you don't have to put dt dt because they match. So ds dt whenever t equals 10 would be 100 times 10. So we would get 1,000. now we have all our pieces that we need to plug in so we can solve, right? For d theta dt. So, we would have secant squared of 1.19028 d theta dt equals 1 over 2,000 times 1,000. Now here, we can't do secant in our calculators. All right, we can't type that in. So what would we have to do instead on our calculator? 1 over cosine squared. So whenever you do that part, make sure that you've got to be very careful. It might actually be best. Let's see. Let me go ahead and do tangent. Oh, no. Tangent inverse of number. Oh, hit that green button. All right, and then do. I would probably do cosine of that number. And then I'd square it. And then I'd do 1 over that number. If you don't get your parentheses right, if you do it the other way, you just be careful whichever way you do it. 1 over that answer. So I get 7.25. It is. I didn't realize it would turn out so nicely there. 7.25. D theta dt is going to equal 1,000 over 2,000 is 1/2, so I'm going to go ahead and make that decimal, 0.5. We're going to divide both sides by our 7.25. So 0.5 divided by, I'm still going to go up here and use that number. I'm afraid it was actually, if you look, it was actually rounded some. It just is really close. Because whenever you have something like this, it's unlikely that it really rounds. Yeah. But you got so many 9s here, the calculator had to round it to 7.25. So I'm going to use that. I don't know that it would make a difference if you use 7.25. So we get 0.0689. I'm going to round that to a 7 there. And that is radians per second on these, I believe. It wouldn't have made a difference if we used 7.25 there. You would be okay. Just know sometimes the calculator does some rounding. Be careful with it. As long as you're correct within 3 decimal places, they count it right on the AP exam. So, but it has to be right within 3. So at that moment, the camera is moving at 0.06897 radians per second. But if you wanted to know, like, the next second, that's changing, because at the next second, it's going to have to move again, right? So it's a pretty complicated formula to make sure, especially if you're, like, zooming in and wanting to stay right on the rocket. Now, a lot of the launches, you know, they are at a much wider angle, so eventually it's just sort of like a spot up in the sky. But if you were wanting to stay right on the rocket as it moved up, if you were zoomed in so that we could see it really closely, then it's really easy for that to get out of your view really quickly. I would like to know how this would work with, like, astronomy sort of stuff, because I got my husband, like, a telescope. It's not a very good one, I don't guess. But I got him that for Father's Day one year because he had been talking about it. He hasn't used it but like 2 times. But the 2 times that we did use it, like, you would get it zoomed in on the moon or wherever whatever star or planet you were wanting to look at, but then the rotation of the Earth, in no time, it was already gone again. Yep. And then you'd have to get it back, and then, so, I think that would be interesting, like, if you were trying to, like, study something and you had a telescope, like, how it would have to be programmed.
How many miles per hour? It's pretty fast.
Yeah, it's very fast. I'm not certain. But anything like that that's moving that you're trying to keep up with could be programmed in this sort of manner. There's also like motion detector sort of things that could work too, probably, but I think it's pretty interesting stuff. I mean, are you going to use it in your daily life? Probably not, but I think it's still pretty. Oh, that's right. Earth is flat.